This is the Math 1111 Zoom meeting. Monday, 11/23, final exam review. I'm going to go over problems that are on the final exam review sheet. Work them out. Oh, we have a participant. Miss Rainwater, yes. I've just started the meeting. You haven't started into any problems on the final exam review sheet. Did you have anything you wanted to ask or go over first?
Can we go over, I was just gonna ask, can we go over number one?
Sure thing. So I'm pretty sure this is what I passed out. Is that correct?
Yes.
Okay. So number one. So the final 1111, final exam review. And we're going to solve, remember these kind of equations, m minus 2 divided by 5, m minus 4 divided by 2 equals m plus 5 divided by 15 and add 2. Now, ordinarily with fraction equations, you'd have to watch for illegal numbers. But that works when there's a letter in the bottom and you could divide by 0, but there's only numbers in the bottom, none of them are 0. There are no illegal numbers here. If you remember that from very first, if you had an equation like 1 over x minus 2 equals 3, then x equals 2, if it comes up, is illegal. And you've got to watch for that, but it doesn't occur on this. So what we're going to do is clear the fractions, multiply by the common denominator, which 2 doesn't go to 5 or 15. Usually start with 15, then you largest one and double it or triple it. So if I double it to 30, 5 goes into 30. All right, we'll get back to them in a minute. 5 goes into 30 and 2 goes into 30, and this is a 1, so common denominator is 30. So we're going to multiply through by 30. If I do it really slow here, I guess a third, like it's a gigantic distributive property. Minus 2 divided by 5, minus m minus 4 divided by 2, m plus 5 over 15, and add 2. All right, so if you remember how this works, you cancel your number into your common denominator and multiply through. So 5 into 30 leaves us 6. There's 6m minus 12. Are we going too fast?
Not yet. I think it's good right now.
Okay. All right, so I'll put a 30 here rather than doing it in my head. So if I go 2 into 30, leave a 15, I'd have a negative 15m, but a plus 60. Negative 15 times negative 4, positive 60. You really got to watch your signs. Put a 30 here. 15 into it will leave a 2. That'll be 2m plus 10. And don't forget to put a 30 at the end. 30 times 2 is 60. So there's the, call it the equivalent equation, no fractions. The fractions are gone, and now there's no m squared anywhere here, so it's a matter of collecting all the m terms to the left, numbers to the right, and finally divide by whatever's multiplying by m. Any questions getting this far?
No, that actually helped a lot.
Okay, sure thing. Let's see, I guess 6 minus 15 be negative 9m. Negative 12 adds 60, what do we have, 48. On the other side, 2m adds 70. I'll take the m's to the left, so minus 2m, minus 2m. There's a negative 11m, add 48, 70. Minus 48, minus 48. They're going to be negative 11m. I could punch it, or you can look on the key. If you, we got 70 minus 48, 22. Oh, it's going to come out even. And so finally divide by negative 11, and you're where m will be -2.
All right.
All right, questions about that?
Not really. That actually, I was so confused on that one. That really helped clear it up
Okay.
because I could not remember the common denominator. I'm happy that made more sense.
Right. Well, it is possible to do it with the fractions in. I call it the I love fractions method, but you have to combine everything with fractions rule. So you're going to get like a -2/5 here, and you got to combine that with your 4/2, and then a 1/3 over there. 5/15 is 1/3. I mean, yeah, if you can combine all those fractions, help yourself.
Oh,
But
no.
I would prefer to clear them and make everything whole numbers. It seems a lot easier.
Yeah. Do not love fractions.
Okay. Let's see. Do you have any others you've looked through and would like to see, or?
Let me look through again. I know a lot. There's a lot in the back half that I'm definitely got to work on because I was struggling with those on the test.
Okay.
I think the next one I had marked was fifth. I think it was 15. I don't remember. 17.
17. Okay. Yeah, tougher domain problem here. Find domain. Root x squared minus 9x and minus 10. All right, so with the square root, you want to set this greater than or equal to 0. If you remember the square root, basically it's on a top, there's no bottom, so it's greater than or equal to 0 because you can't do square roots of negative numbers. All right, remember if it was 1 over the square root of x squared minus 9x minus 10, it'd only be greater than 0. There'd be no equal to if this is on the bottom of a fraction, because then you'd be dividing by 0. I hope you remember that little technical detail.
Yeah. Okay. So if it's
It's
on the top, it has.
not ringing a bell. It's
Oh. That makes. I think I'm remembering it now.
yeah, it's square root. Like if I really did a really simple one, if I had the square root of x minus 1 and I want domain, then I set it greater than or equal to 0. Well, x minus 1 greater than or equal to 0 means x is greater than or equal to 1.
Oh yeah.
Trying to remind you what domain means. I can only stick numbers 1 or bigger in because they'll give me a positive root. A 0, I can use 1 because it's on top, and that 1 minus 1 square is 0, square root of 0 is 0, and then I can use anything bigger than 1 because it'll stay positive. But if I use like x is -1, then I get a square root of -1 minus 1. Square root of -2 is an I. That's illegal. Okay, oops, so some message came across. Okay. All right. So yeah, this one's more complicated than this. It's the same principle, but it's more complicated because you've got the square letter and number. So you're going to want to factor it, x minus 10, x plus 1. And basically you're going to solve x minus 10, x plus 1 greater than or equal to 0. The answers out of this will be the domain. Well, x is 10 and x is -1. And when I put those on the number line, -1 comes first, 10 comes second. And do you remember open or closed circles?
Those are closed circles.
Closed. Because you have the or equal to. they are individually answers, but there's one of these interval, or maybe two, multiple intervals between these are also answers. If it was straight equals, these are the only answers, but it's not. It's got an inequality. So that's when you test. I guess we can try -2. So does -2 minus 10, -2 add 1, greater than or equal to 0? Again, that'll be a negative. This will be a negative, greater than or equal to 0, and ways multiply to a positive. So yes, this is in the domain. Numbers over here give a positive. Are we going too fast?
No, that's perfect.
Okay, we can try in the middle. Let's say 0. We have 0 minus 10, but 0 add 1, greater than or equal to 0. Well, this is negative, this is positive. So a negative times a positive is a negative. Greater than or equal to 0? No. Numbers, any numbers between -1 and 10 are going to give negative out of this. Square roots of negatives are i's. Can't be in the domain. That too fast?
No, that's good.
We'll try 11. You can probably see 11 in your head. 11 minus 10 is positive. 11 add 1 is positive. You can probably see it without writing it down that, yeah, this is going to work, but I'll just finish it up for anybody who watches this later. 11 minus 10, 11 add 1. Yes, you got a positive times positive. So now you can write your domain in interval notation right off the graph. -infinity to -1 with a bracket, because you are including -1. And then you're picking up again with a bracket and 10 comma infinity. Any numbers this side of -1 or that side of 10 and that side greater than 10 are in the domain. They give positives in this function.
Okay.
Questions about that?
The brackets are only solid if the circle's colored in, right?
That's correct. And that comes from being the or equal to.
Okay.
Yep.
That's perfect.
All right.
Think of something else. Can we do number 22?
I heard 22. All right. Find zeros and state multiplicity. Okay. Well, x to the 6th plus 4x to the 5th plus 4x to the 4th. All right, only a 1 there, no 4s all the way through. So really, we can factor out x to the 4th. Factor that out. Big parentheses. X to the 4th times what is x to the 6th? So you'd have to be x squared. In effect, you're lowering the powers by 4. So you'd have a 4x. So x to the 4th times x is your 4x to the 5th. And you'd have a 4. Now, you could use a quadratic formula on this, but it also works by two numbers multiply to 4 and add to 4, which would have to be 2 and 2. X to the 4th, x plus 2, x plus 2. And since those are identical, we can write that x to the 4th and x plus 2 squared. Now, do you see how to get your zeros out of this? you set each piece to 0. X to the 4th equals 0, so X has to be 0. 4 through to 0 is 0. And you see your other zeros, X equal -2. You remember what multiplicity was?
I don't think so.
It was the power up here.
Oh.
So this has multiplicity. The X equals 0 is multiplicity 4. Multiplicity 4. This is multiplicity equal to the square. I don't know if you remember what that meant. It's a technical detail. There's so many technical details, it's hard to make a big deal about them all, but it just meant that these were touching x-intercepts.
Okay.
So whatever the graph looked like, at 0, it's touching, and at -2, it's touching. Now, whether it could be touching down, it's hard to see without the graph, but whereas odd multiplicity meant crossing x-intercepts. Crossing. Not that you probably care about these details, but that's why they're asking. You can tell what it does on the graph, whether it touches or crosses. They didn't really ask for the touching or crossing. So really they wanted you to stop at multiplicity. Did you have another one?
Did I have another one? Yeah, let me look through them again.
I apologize. Can you turn up your volume? Maybe it's my volume. Let me see if it's my volume.
It might be mine because I don't have my mic plugged in. Let me go.
Oh, okay. Well, mine could be up a little more. Okay, so let's see if that helps. Yeah, that seems better. You have another one?
Let's see. Number 25.
Okay. Horizontal asymptotes, vertical asymptotes, f of x, 7x squared plus 2x, and 4x squared minus 9. All right, your vertical asymptote is going to come from setting your bottom equals 0. In effect, it's where you divide by 0, where you're blowing up. So I'm going to have 4x squared minus 9 equals 0. I could move the 9 over, take a square root, or we could factor it. I don't know, you know you're factoring well enough to know that's 2x add 3, 2x minus 3.
Mm-hmm.
And can you tell that you're going to get 2x equal -3 and you divide by 2? So one vertical asymptote will be at -3/2. You see what happens? You change the sign but divide by this number. So the other one is +3/2. So you got a vertical asymptote of positive and -3/2. These are vertical asymptotes.
Okay. All right, that makes sense.
Okay, yes. The horizontal asymptote was a lot more technical. The horizontal asymptote, I don't know if you remember that there were 3 cases.
I don't remember them exactly.
Okay, it's about comparing top power to bottom power. You don't have to write down all 3 cases. I'm just doing it for anybody watching this later who just wants to review this, just in case it's a different case from this one. The top power can be greater than the bottom power. The top power, by the way, we're talking about the lead, by the way, lead. So this lead, this is going to be a case 2. Your top power equals your bottom power. Third case is your top power less than. You remember what happens when your top power equals your bottom power, or has that been flushed?
You divide the constant. and
These
then
numbers,
above.
right? Outstanding.
Yay.
So on this one, yes, the man we hired to flush your brain did a terrible job to flushing your brain. Yes, you remembered. Outstanding. So the horizontal asymptote on this one will be y equals 7/4. Yes, ratio of lead coefficients. That's what you get when they're equal. Ratio of lead. Do you want any reminder what happens on the other cases?
Yes.
All right. Top power greater than bottom. That's like an x cubed over x squared. That's really easy. None. And if your top power is less than your bottom, like it's an x squared over x cubed, that's easy too. That's always 0.
Oh.
Which means x-axis.
Okay. I'm gonna take a picture of that. Or
Okay.
actually, I can come back and watch the video and get it.
Well, if you have a watch and know what time it is, you can pretty much pinpoint. You don't have to watch the whole thing looking for it, right? You can fast forward to it.
Yep.
We started pretty much on time, right at 12. So
Yeah, I didn't know if anyone else was gonna be here, so I made sure I got here right on time.
okay, sure thing. Yeah, usually, yeah, you're not really having to elbow anybody out. There might be a few more people show up at 9 o'clock.
Okay, I might be able to make that one too.
Oh, okay,
That's great.
sure.
I'll have to see.
Yes. Do we have another one?
28.
I'm sorry, which one?
28.
28. Okay, this came out of 110. Yeah, these very just directly kind of problems. I don't know if I want to copy this down. A lot of words.
Might just have to read that one.
Yeah, just read it. I'll try to keep it here on the screen. All right, so a lot of times, sometimes they get the letters directly from words in the problem, which is the way I wrote the key. Sometimes you just like to just do Y's and X's, but then you got to remember what Y and what X is. I guess I'll just do the letter here. So current, we'll use C. I'll just paraphrase this. Varies directly as voltage V and inversely as resistance R. These are electrical terms. Okay, so if you remember that varies directly, let's see. Oh, I knew ECT, there we are. When you had that varies direct, used an equals where the varies was, and you always brought in a K for a constant of proportionality. So a formula for this, C equals K, the V is on top because that's direct, inversely went on the bottom of the fraction. So that's where I'm getting this formula right here. That's, if you want to bust this into steps, that's sort of step 1, be able to write the formula. In step 2, they tell you C is 9, V equals 90, R equals 10. So that's enough info to find K, even though they didn't directly tell you to find K. I copied this straight out of the book. But that'll allow you to find K, and then we can plug in the bottom numbers and ultimately answer their question. Are we going too fast?
No, this is good.
So 9 for the C equals K, 90 for the V, 10 for the R. All right, and then you're supposed to know what algebra to do to get to the K. So we multiply both sides by 10. That'll clear the 10s. 90 equals basically 90K. You tell K is 1. Divide both sides by 90. 1 equals K. All right, but now we can go on sort of and answer their question. Now they're telling us, answer question. Find current, C, B equals 160, R equals 5. Getting that from here. Find current, V equals 160, the resistance is 5. So plug in, it's just plug and chug, but it's really going to be arithmetic because what they want me to find is out here by itself already. C equals then 1 for the K, 160 for the V, divided by 5. Well, I can punch that out on the calculator, just 160 divided by 5.
32.
32. There you go. 32. All right. There another one?
Can we do 32?
Okay. All right. Basically, expand, right, is a sum or difference. So we have a straight log, that'll be base 10, this is 32. Square root of d squared add 1 is divided by 10,000. So if you remember your laws, you go log of the top, subtract log of the bottom. They gave it to you in terms of A's and B's. Do I need to write the general formula down, or is this okay?
That's okay.
Okay. Well, then the square root's in a half power, so that's the third law. I can go to the front, so that's in a half. A log of d squared plus 1. And then this is a base 10, and 10,000 is 10 to the 4th. So you can directly work that out. The log base 10 to the 4th is going to be directly 4. You can punch it as well because you do have an LOG key. But that's where we get this.
All right.
Did you want to see B?
Yeah.
Okay, B is kind of the backwards problem. This was A. B takes a log base 7 of 98 and subtracts log base 7 of 2. You really want to just combine this. Well, you see up here, your log of top minus log of the bottom, which is basically this log of top minus log of the bottom, which means it combines back. Positive one's on top, the negative one's on bottom.
Okay. That's better than
All right, then they want this simplified. 98 over 2 is 49, so it's been cooked to go further, 49. And then 49 is 7 squared. 7 squared. And can you see you finally get 2? These will undo.
Oh yeah, they will. That's perfect.
Okay.
Exactly what I need.
All right.
Let's see. I don't know if I missed one. Let me look back. Can we go back to 24?
Absolutely.
I just can't remember how to write them.
Yeah. This is kind of a longer one. It's just kind of your ideal FOIL problem. Just goes nuts with foiling here. Okay, at 24, you want a degree 3 polynomial. You understand what that means? That means you want like something x cubed. Who knows how many other pieces it'll have, but your lead piece is going to be something x cubed. I just assume there's other pieces. But that's what you're going to wind up with. That's a degree 3 polynomial generally. All right, zeros. I tell you negative 7i and 3. All right, remember, as a general rule, your zeros are kind of the answers to this. If you got a lead power 3, you're going to have 3 answers. Remember, just an x squared, a quadratic, you have 2 answers. If you only have an x, you get 1 answer. So they've only really given me 2 of the answers. So the third answer, there was a complex zero theorem in chapter 3. If they give you a imaginary answer and a sign on it, the other sign of this is always the other answer. In other words, the other zero is 7i. Again, one of those technical details may have got glossed over. Do you happen to remember that?
I don't remember the name of it.
It was complex zero theorem, it was called.
That was it.
Yeah.
It started with a C.
Right. All right, so this means I can start creating my formula, my polynomial. Well, I can put the x minus 3. Remember, if 3 is a 0, your factor for that is going to be x minus that number. If this was negative 3, it'd be x plus that. And you always switch the sign for the factor. You remember that?
I think so.
Okay. That's so you can put in 3 and you get 3 minus 3, which is 0. That's why it's called a 0.
Okay.
Okay. If it's negative 3, your factor would be x plus 3. The sign switches when you go to the factor. So you can put in negative 3 plus 3 and get 0. All right, so that is the factor for the 3. You can play the same game with these others. You'll have an x minus 7i. So you can put in 7i here, 7i minus 7i is 0. I'll go ahead and show you all the steps. You'd actually have an x minus negative 7i for this one. And you see how your 2 negatives turn that positive?
Mm-hmm.
You'd have x minus 7i and x plus 7i. So your negative 7i plus 7i here is 0. Is this okay getting this far?
Yes.
The rest of this is just a gigantic, nasty foiling problem. But I'll give you a clue to how you're going on the right track if you can remember this. I tried to say this when we were going through this. There will be no i's in the final answer. So if you wind up with i's in the final answer, you're screwing up. All right. You cannot do this 3 at a time, so you can pick any 2. I think it goes a little easier if you do the I pieces first and hold this, that, you know, work this out as simple as you can, then bring this one in. So I'm going to play it that way. Are we ready to charge ahead?
I think so.
Okay. So it goes, you know, x squared. You'd have a positive 7ix. There's round 1. Then a negative 7ix. And a negative 49i squared. Negative 7 of 7 is negative 49. I times I is I squared. All right, can you tell your 7ix minus your 7ix? See, that's going to vanish. And do you remember that an I squared is equal to negative 1?
Yes.
So if I put in a -1 there times -49 turns +49 plus 49. And my eyes are gone. So if I do this correctly, I should have it correct. And again, there'll be no eyes in the final answer. Are we ready to finish it?
I think so.
Okay. X to the third plus a 49x, round 1, minus 3x squared and minus whatever the heck 49 times 3 is. I have it on the key. 147. And this is perfectly valid, but of course it's slightly out of order. So just to make it neater, we'll make it x cubed minus 3x squared and add 49x and minus 147. No i's in it. And if I plug 3 in it, you'll get 0. If I plug 7i in it and you got the patience to work it out, you'll get 0. You can't do that directly on the calculator. And negative 7i in it. You got the patience to see any of that, or do you believe?
I believe.
Okay, sounds good.
Just whoop.
Yeah.
Yeah.
Just think, hang with this, get your credit, move on with your life. You'll probably never see this ever again. But you got credit for college algebra, which they required you to take.
I enjoyed it while I had it.
Okay.
Thank you for helping.
Well, sure thing. Is there any others we can show you?
I think that's what I was having the most trouble with.
Okay.
I'll look through this one more time just to see if this is it.
All righty.
I think I'm good.
Okay. Well, very good. Don't feel
Perfect.
okay. Sounds good. Don't feel obligated to hang around. I may pick another one like 23. You hadn't done 23, long division or something, just to stretch this out to about 45 minutes. Convince my bosses I'm earning my money.
I'll stick around for
But,
23.
you don't have to stick around. Maybe I'll just do 23 and I'll call it.
Okay.
23 is a long division. Got a pretty darn long formula next to the fourth formula with all the pieces back to 12 there. I'm going to divide it by x minus 3. It looks like it goes evenly according to the answer. Let's see if I can get it to work. 23, long division. Take x minus 3 and divide it into u minus 11x squared, add 11x, add 12. All right. If you remember how these work, but you basically ask yourself, x times what would give me an x to the fourth? And you can tell I'd be an x to the third. And then you multiply back in both pieces. That would give you x to the fourth minus 3x to the third. And then the secret to it is subtract, but it distributes. Lead piece always cancels. A negative, subtract negative, that'd be negative, add 3, looks like it'd be 2x cubed. And then all the other pieces come down. This is going to be a long one. Are we going too fast?
Nope.
I'm not looking at the answer, so I'm seeing if I can do it from scratch. X times what is 2x cubed? That'd be 2x squared. 2x squared times x, 2x cubed minus 6x squared. Subtract. Negative 11 minus 6 be a positive, no, I'm sorry, be a negative. Be careful. It'd be a negative 5x squared plus 11x plus 12. All right, so x times what's a negative 5x squared? That'd be a negative 5x. Negative 5x squared, add 15x. Subtract, parentheses there, lead piece cancels. 11 minus a 15, negative 4x plus 12. X times what's a negative 4? 4x would be a negative 4. So there's negative 4x and a plus 12. Yeah, goes evenly. When these work out identical and then you subtract them, your pieces cancel and give you 0. And yeah, if I took this quotient times this in a FOIL, I would come back to this.
No, yeah, that one didn't work out perfectly.
That one works out clean because it was cooked to do that.
Yeah. I like that one.
Okay. Did you come up with anything else, or are we ready to call the meeting?
The last question, 33.
33. Okay. All right. You want to see both parts?
Yes.
All right. Solving log equations here. 33a is not long, pretty short, but 33b is going to be a lot longer. All right, 33a, log of x plus 47 equals 2.7. Again, log means base 10. So I'm going 10 to a log x plus 47, 10 raised to the 2.7. So this will undo, leaving the x plus 47. I can work this out now, write it down, or I can wait till the end because all I got to do is subtract 47. I think I'll just wait till the end. 2.7 minus 47 minus 47. All right, so it'll be 10 raised to the 2.7 power, subtract 47. You can tell this is going to be over 100. In fact, it's going to be not far from 1,000. 10 to a third's 1,000, so 2.7 short of 3 would be a fairly big number. 10 raised to the 2.7 and subtract 47. Yeah, it's 454.187. Questions about that? The real trick to it is recognizing base 10 and doing 10 to a power.
Okay. Yeah, I'm gonna have to remember the base 10 because I think
Yeah.
I hope I get that.
LOG is base 10. And if you forget, it's right there on your calculator. LOG is base 10. They've paired it. LN is base E.
Oh, I didn't even notice that.
Yeah.
That's awesome.
Yeah, that's the 2 they give you right on your calculator. You have to, other bases like log base 2, they have to write the 2 of the exponent that it undoes. And it's not on your calculator. You have to write the base of this that it undoes. You still want to see B?
Yes.
Okay. $11 to the 1 minus 8x equals 9 to the 2x add 3. Yeah, this would be a little longer. Again, you've got a base 11 here, a base 9. You could use either one on both sides, but I don't mess with it. I use LN just because it's on the calculator. So I use an ln of 11 to the 1 minus ax equals ln of 9 to the 2x plus 3. And you realize that they don't directly undo, right? Base e doesn't undo base 11, base e does not undo base 9. So you put these exponents in the front with the parentheses because it's multiple pieces. 2x plus 3 ln of 9. Are we going too fast?
No.
Okay. So it gets, you know, you can play this a lot of different ways. Yeah, I mean, I could punch the ln11, punch the ln11, and then you got to write down nasty decimal here, nasty decimal here. And then you got to distribute through, collect your x's to the left, numbers to the right. You can play it that way. I prefer to just go ahead. You can cut it down to one nasty decimal. If you pick one of these and divide by the, say, the ln of 9, and that leaves you your clean 2x plus 3. Now you're going to get a nasty decimal here that we'll have to distribute, but at least it's only on one side instead of both sides. Mm-hmm. That makes any difference. An ln of 11, divide that by an ln of 9. You're at 1 point, my screen's getting, I think that's 1.09. Yeah, those blips on the screen. Can't clean my screen. 1.0913, we'll call it. All right, so the rest of this is just distributing this. So 1 point, which is easy on the 1, that's just 1.0913, subtract, and then I got this times 8. 0913 times 8. 8.7304, 2x plus 3. And now, I don't know, can you do it all at once? You're going to go minus 2x, minus 2x. You don't really need to punch this because it's straight. That's 1.0913, subtract 10. 304x equals 3. Is your 8 minus 2. Since they're both negative, they're going to add. Decimal carry along. Are we going too fast?
No, that's perfect.
Okay, move the 1.0913 over by subtract 13 over. All right, so unless you're a real genius, maybe you want to punch that. 3 minus 1.0913, 1.9087, negative 10.7304x. And yeah, it's got nasty. It's really the same thing, just, you know, numbers a little longer, a little nastier decimals. Negative 10.7304 divided by negative 10.7304. And so it's going to wind up negative 9087 divided by negative 10.7304. Negative 0.177, maybe we'll call it 9. Please tell me that's what I have on the key. Oh, I got the key right here. Yes, it's a miracle. Oh. Amazing how many times you do something right a long time, then you mess it up the next time you do it. That's math for you. Anybody can make a mistake at any time.
Trial and error.
Yeah, absolutely. Really embarrassing is when I'm helping my son and I make a mistake helping my son. He does it right and I don't. That's embarrassing. He's in 6th grade. That's really embarrassing. It's happened a couple of times.
I passed the point where my parents could help me very early on, so I've been on my own for forever now.
Oh, goodness. Okay. Is there anything else I can help you with?
I was just going to ask, for natural logs, when you're solving something like that, the exponent's always going to go back in front of it, right?
Yes, that's on any log. That's a law of logarithms. There's nothing magical about natural log. So you can have a natural log x squared, that's twice natural log x. You can have a log x squared, that is 2 log x, and you could have log base a. They usually use an a in general, but I could have 4 of x squared is twice log base 4 of x. It does not matter what the log is. Any power on its argument like that goes as front. Now, do not confuse this with log of x and they put a squared here. This is different from this. This 2 cannot go to the front.
Because it's outside.
You get the difference? It's the difference between being the square being on the entire log versus just on what the argument is. Maybe we should, for clarity, we should put that argument in parentheses. I don't know if that helps. Or you could write ln of x squared like this. Let's see it. This would be equal to twice log of x. But not log of x, put parentheses in and square. Does that help?
That helps a lot.
Okay.
Thank you so much.
Your thing.
That helps a lot. Thank you so much.
Your thing.
I think that's
it.
Yeah, that's all I had.
All right. Well, very good. We will be back at 9 o'clock if anything else comes up. And yeah, well, this has been long enough to convince them I earned my money today, 50 minutes. So. All right. Sure thing. And if we don't see you tonight, you have a happy Thanksgiving.
All right. Thank you.
Sure thing.
Bye.
Bye.